Topic 5 is the halogenalkanes. The homologous series called the halogenalkanes have the functional group CX, where X can be fluorine, chlorine, bromine, or iodine. Halogenalkanes can be classified as one of the following based on the other atoms bonded to the carbon atom to which the halogen is bonded. If there is only one carbon atom bonded, it is a primary halogenalkane. If it has two carbon atoms bonded, it is a secondary. And if it has three carbon atoms bonded to the carbon atom, which is bonded to the hydrogen, it is a tertiary halogenalkane. Halogenalkanes are named as substituted alkanes, with the position of the halogen indicated by numbers when necessary. Simple halogenalkanes with up to two carbon atoms and one halogen atom do not require a number. The boiling point of the halogenalkanes derived from methane is shown in the table. We can see that the boiling point will increase as the mass of the halogen atom increases. The increase in boiling point is due to the increase in the number of electrons in the halogen atom, which leads to greater van der Waals forces between the molecules. As with the alkanes, as the carbon chain gets longer, the boiling point of the halogenalkanes increases. If we look at branched isomers, we can see that the greater the amount of branching, the lower the boiling point. This is because the molecules cannot make as much contact with each other. The large bromine atom in the middle of the molecule in 2-bromo-2-methylpropane reduces the contact between the hydrocarbon chains, and this reduces the van der Waals forces of attraction between the molecules. Other physical properties of the halogenalkanes are that they have a sweet, sickly smell, they are immiscible with water, and form two distinct layers. We are now going to look at the reactions of halogenalkanes, which involves a new mechanism called nucleophilic substitution. We will leave the laboratory preparation of a liquid organic compound, such as a halogenalkane, from the alcohol to the next topic. In this topic, we are going to meet nucleophiles. The definition for a nucleophile is it is an ion or a molecule with a lone pair of electrons that attacks regions of low electron density. Here are some of the nucleophiles we are going to meet in this topic: hydroxide ions, bromide ions, and water molecules. So in these examples, you can see you have both ions, the hydroxide ion and the bromide ion, and molecules, you have water. In halogenalkanes, we need to remember that the carbon-halogen bond is polar. The greater electronegativity of the halogen attracts the shared pair of electrons, so it becomes slightly negative. We have a polar bond. The table gives you some of the values for the electronegativities of the different halogens. In this topic, we are going to study a new mechanism, nucleophilic substitution. If you look at the diagram that has been drawn, you can see again you have dipoles, curly arrows, and full negative charges. In the first stage, the nucleophile has a lone pair of electrons, and the carbon-halogen bond has a delta positive and a delta negative assigned to it to show that it is a polar bond. The curly arrow is drawn from the lone pair to the slightly positive carbon atom, and the second curly arrow shows the shared pair moving on to the halogen. The polar carbon-halogen bond breaks heterolytically. At this point, a new bond is formed between the carbon and the nucleophile. The halogen now has its own electron back, plus that from the carbon atom. It now becomes a negatively charged halide ion, and it has left the molecule. Here are some examples that we have to study with nucleophilic substitution. It is important to know the equation, the conditions, the product, and the nucleophile in each case. The first example is the reaction with aqueous sodium hydroxide solution. In this case, we are substituting the Br, or the halogen in our halogenalkane, with the OH group, the hydroxide group. And in that case, we will form alcohol. We can also do a similar reaction, but instead of using a hydroxide ion, we can use a water molecule. This reaction is much slower as water is a poor nucleophile, but we get the same product as we do in the nucleophilic substitution with the hydroxide ion, in that we get an alcohol. With nucleophilic substitution, we can have two different mechanisms, and this will depend on whether we are starting with a primary halogenoalkane or a tertiary halogenoalkane. Let's look at the SN2 mechanism using a primary halogenoalkane. As the hydroxide ion approaches, it uses its lone pair to begin forming a coordinate bond with the electron deficient carbon in the carbon-bromine bond. This is a slow step of the reaction, and it involves two species. A transition state is formed where the molecule has two weak bonds with the attacking nucleophile, the OH- and the leaving group, the bromine. There is a total of 5 bonds on the carbon atom, so the transition state is highly unstable and cannot be isolated. It also has the full negative charge, which has come with the extra electron on the hydroxide ion. As the coordinate bond continues to form between the carbon and the OH, the carbon-halogen bond then breaks and we form our product and a bromide ion. This mechanism is called SN2 because in the slow step of the substitution, the nucleophilic substitution reaction, it involves two species, the halogenoalkane and the nucleophile. We are now going to look at the SN1 mechanism, which occurs in tertiary halogenoalkanes. In the first step, there is heterolytic fission of the carbon-halogen bond. 2 electrons in the bond are transferred to the bromide ion, and a carbocation is formed. The carbocation that is formed is stabilized because we have 3 methyl groups donating electrons to the positive carbon. This first slow step of the hydrolysis only involves one molecule. If we move on to the second step, the carbocation then is open to attack from nucleophiles. The nucleophile attacks the positively charged carbocation and forms the alcohol. This is called an SN1 reaction because it is nucleophilic substitution, but the slow step involves only one species, the tertiary halogenoalkane. We also have to study some other nucleophilic substitution reactions. In this case, we are using cyanide ions, and the general equation, the equation for the nucleophilic substitution of cyanide ions in bromoethane is shown. In this reaction, we produce a new product called propane nitrile. If you have a look at the equation, you can see that the chain length has increased from 2 carbons to 3 carbons. It is important to note the conditions. The halogenoalkane is dissolved in ethanol and it is dropped into an aqueous solution of sodium or potassium cyanide, and the mixture is heated under reflux. Another nucleophilic substitution reaction that we can study is using ammonia as a nucleophile. In this case, the product will be an amine. The conditions for this are aqueous ammonia in ethanol, and it is heated in a sealed tube. It is important to use ammonia in excess, otherwise your product, the amine, can act as a nucleophile and you can get further nucleophilic substitution reactions. Earlier in nucleophilic substitution, we met hydrolysis where water is used as the nucleophile. We can study the ease of hydrolysis of halogenoalkanes by following how quickly the halide forms. If you remember back in Unit 1, we were able to do precipitation reactions using silver ions and halide ions. When our halide is formed, if we have silver ions in the reaction mixture, we will form a precipitate. If you remember from Unit 1, the different halides produce different coloured precipitates. The investigation into the relative rates of hydrolysis of halogenoalkanes can be done practically as follows. This preparation can be found in the SEA practical book. When we carried out the reaction, the yellow precipitate formed first, followed by the cream precipitate, and finally, after a significant time, the white precipitate. We can explain this if we look at the bond enthalpies of the carbon-halogen bond. If you have a look at the table on the right, you can see that the carbon-iodine bond is the weakest and the carbon-chlorine bond enthalpy is the strongest. So the major factor in reactivity is the carbon-halogen bond enthalpy. The rate of hydrolysis of primary halogenoalkanes increases as the strength of the carbon-halogen bond decreases. This table shows a reaction summary. The first three reactions are nucleophilic substitutions. What is interesting is if we look at our reagent as potassium hydroxide, if we change the conditions from water as the solvent to ethanol as the solvent, we get a different type of reaction. Instead of getting nucleophilic substitution, we get an elimination reaction and form an alkene. When a halogenoalkane is treated with hot ethanolic potassium or sodium hydroxide solution, the type of reaction that occurs is an elimination. In this case, the hydroxide ion is not acting as a nucleophile, but instead it acts as a base, removing a hydrogen from the carbon beside the carbon that has the halogen atom. The products in this reaction are the alkane, water, and either sodium bromide if you use sodium hydroxide or potassium bromide if you use potassium hydroxide. When we look at an elimination reaction, we need to look at the halogenoalkane we are using. If it is symmetrical, and the example here is 2-bromopropane, we will get one product, prop-1-ene. However, if we use an unsymmetrical halogenoalkane, the example here being 2-bromobutane, we will get more than one product. If we look at this reaction, you can see the product will be but-1-ene, but if you look at the other reaction, you can see the product is but-2-ene. This is because the hydroxide can take the hydrogen from either side of the bromine, giving us two different products.